Jaskaran Sodhi.
Here is the outline of our presentation today, and Salem now will present the introduction.
The main problem facing researchers is determining temperature profile of flame or reaction. Thermocouple is used to measure temperature, at one point only, and this is trusted. So thermocouple measures temperature at one point only, and is trusted. So in one point only, and is trusted. So using a new technique that will help which is the calibrated camera, and MATLAB codes that will help us to do the process. Here is the schematic of our process. First thing that we will capture the flame, then we will computation it, then we will get the temperature profile. For application, our procedure will be documented and going to be offered to the research laboratories, boiler industry, where they regularly need to monitor the temperature. Further research when studying combustion or reaction.
So what does pyrometry mean? Pyrometry is a Greek word where pyro means fire and metry means metal. So two-color pyrometry is a technique relies on the ratio of two intensities using two different wavelengths and plugging these two wavelengths in Planck's law to obtain temperature profile of a flame. So we use two-color pyrometry methodology with high-speed cameras, which will be calibrated to obtain temperature profile by converting the pixel intensities to temperature profile. But before explaining the theory behind our project, we should know the difference between radiance and irradiance. Radiance is the radiant flux emitted by the flame, while radiance is the radiant flux received by the camera sensor. When a ray of light travels through a participating media in any direction, it loses energy by absorption and gains energy by emission. So the total spectral intensity for green color will be divided by the total intensity of red color to solve for the temperature equation. Here is the temperature equation we got, and as we see from the denominator, the IG, which is the green intensity over the red intensity, epsilon lambda is the spectral response for both green and red colors. C sub lambda is the shifting constant for both green and red colors as well, which means, so shifting constant means the value will be used to shift the relative response function to a physical response function, which will be explained by Ahmad in camera calculation later on. Since the directional distribution of surface emission varies depending on the nature of the surface, we obtain the first equation from heat and mass transfer book, and we obtain this equation from heat and mass transfer book, and we made the assumption that it's a diffuse emitter as a surface as shown in the figure, which means the intensity of emitted radiation is independent of direction. So we solved the first equation and we got the factor of pi as shown in the second equation, where EB is the actual irradiance, which will be explained by Jaskaran later on. Here is the spectral emissivity equation, where K is lambda is the absorption coefficient and L is the flame path length. There are several ways to calculate absorption coefficient, but the most efficient way or equation is this equation, where N and K are real and imaginary parts of complex refractive index. There are some assumptions we made in our process based on our research. So the first one is our flame is an optically thin flame, which means it just emits energy without absorbing any energy. The second assumption is its soot particles have homogeneous soot properties, And also, the soot radiation has the dominating contribution in our process to the total heat flux. Also, the lighting variation will be ignored in our process because the lighting of the shutter speed will be very high.
So for the equipment we are going to use, we'll use a camera, tungsten lamp, and narrow bandpass filter. For the camera that we are using, we will use X3 with a resolution of 1440 pixels, which means a high-speed camera with adjustable shutter speed, and it can take images at 400 frames per second. For the tungsten lamp, we are using SL.cal, which is a tungsten lamp with a calibrated data such as intensity for different wavelength range from 350 nanometer to 1100 nanometer. And we're also using a tungsten lamp to calibrate our camera to find a constant. For the narrow bandpass filter, it's used to filter our wavelength, such as by letting certain wavelength to pass and block other. Also, the filter will give us the peak wavelength for both color, red and green. We are burning a hexadecane, which is geometrically uniform, and it's a sooty flame, and the temperature range of it from 1000 to 1800 Kelvin.
So now I'll go over the camera calibration and how we're going to do that. And the three topics that I'll cover are digital pixel intensity, its relation to exposure, and relative exposure. So any camera, when it takes an image, it takes it through its sensor, which have photodiodes behind them. So any photons that it receives on the sensor get converted to a digital pixel intensity. And as you can see, this image was taken by Luigi during his droplet experiment, and we can look at the pixel intensities for any point in the image in the grid. So to calculate temperature, we need a one-to-one mapping between this pixel intensity and physical radiation, which we have to use in the temperature equation. So in a research paper published by Debbeck and Malik, they defined this pixel intensity as a function of exposure, where exposure is the product of irradiance and exposure time. So basically, F is a transfer function which transfers that exposure to a pixel intensity. And they further defined this function to be smooth and monotonic, which means it constantly increases, so can be inverted. So what we do with this equation is we take the inverse of this equation, as you can see in the second equation, and we take the logarithm of it just to make our calculations easier, and we end up with the fourth equation. And from now on in these slides, we'll call this log of F inverse as G star, and this will be the equation that we'll solve for. Anywhere in this slide where you see a star, that means it's at the camera sensor site and not at the flame. So all the data that will be calculated here will be at the sensor, and we'll have to calibrate it to get the data for the flame. So the image characteristics. So we are going to use an 8-bit image, which means there is a pixel intensity range of 2 to the power 8, so 256. And it starts from 0, so it goes up to 255, where 0 is the black color and 255 is the white color. So this equation that we have to solve, as you can see, there are two unknowns in this equation, which is the function G star and the irradiance that we have to calculate for. So how are we going to do that is we're going to define a constraint. Since we are doing everything which is relative at the camera sensor, we can define any constraint, and later on when we calibrate it, it will be removed anyway. So we define this constraint to be G star at Z of mid equal to 0, where Z of mid is the midpoint between the maximum and the minimum pixel intensity. And to solve this equation, we are going to use singular decomposition method, singular value decomposition method. What it means is like it solves for a matrix which is overdetermined. And the condition we need to use for that is n times b minus 1 should be greater than z max minus z min, where n is the number of pixels, b is the number of photographs, and z max minus z min is 255. And so if now further going in the slides, I'm going to use 7 photographs to do that calculation. So if we put 7 in the place of p in the equation, you get n greater than 43, which means we need to have 43 pixels to use this method. So as you can see, these are 7 images. We obtained them from an open source, and the image on the left hand side is the one that's receiving the most exposure, so it's bright, and the image on the right hand side is getting the least exposure, so it's dark. We define our pixel grid. Since we cannot, we cannot take the resolution of the complete image because it will be too many pixels, so the computation will be too expensive. So we define a grid ourselves, and at these points on the grid, the pixel intensity will be evaluated. And the grid resolution is 512 by 768, and since we have 7 images, it's a product of 3 and it's definitely greater than 43, which means we can use the singular value decomposition method. So the equation we have to solve for, and the equation on number 2 is the objective function, which is an error function. If you move the two terms on the right hand side of the first equation to the left hand side, you get the first term in the objective function. So it will go to 0 as it has to satisfy that digital pixel intensity. And lambda in the second equation is a smoothness factor. Since pixel values are discrete and there are no values in between like 1 and 2 pixel, we use this smoothness factor to make it like as a function so that it's continuous. And another thing you can notice in this equation is the weight function. And why do we use weight function? Because there will be images which will be either underexposed or saturated. So the weight function that we decided to use is a hat function, where as you can see for pixel intensity of 0, the weight value is 0. In the middle, it's maximum, and on 255, which is the underexposed part, it's again back to 0. So now that we can use that method, we'll get that, and we'll get our results from our MATLAB code for irradiance values for all the points on the grid in a pixel for all the images. But what we want is just one single image and one value of irradiance. So for each point in that image. So what we do is we take the average, which is this function, the second equation, for all the pixels throughout the image. So J is the index which goes from 1 to P, where P is the number of photographs. And what we end up with is the SDR image from all these 7 images, which combines the data from all these 7 images into just one images. This is what our mobile phones, any mobile phones nowadays that have an SDR function do to take an SDR image. Our results for camera response function look like this for all 3 channels. Now every time a camera takes an image, it has 3 channels, red channel, green channel, and blue channel, which are the 3 primary colors, so that any color can be created and can be there in an image. And we are doing 2-color pyrometry, so we need to choose 2 colors. We choose red and green, and we don't choose blue because blue is noisy, prone to artifacts, and also that red and green are closer to the infrared region, so they will give us more accurate data. Now that we have solved for the irradiance at the sensor, what we need is the physical radiance at the flame. So we need some calibration done. And our radiance at the flame will be the irradiance times a constant. And if we take a logarithm of that equation, we choose to call the log of eta the C lambda, which is the shifting factor Saad talked about earlier in the slides. And this is what will be solved for, and Ahmad will explain the experimentation behind it.
I'll just go and say, if we want to shift the relative radiance to physical radiance, we have to find shifting constants. In our experiment, we will find 2 shifting constants. One with filter, which is called C lambda, and one without filter, called CI. Since the wavelength range that passes the near-bandpass filter is lower than the range that we detected for the red channel or any channel in the camera, so we have to correlate CI with C lambda in order to make the camera take an image as there's a filter in front of it, even without. Because changing the filter while doing the experiment is impossible due to the frame will not be stable. So in order to get C lambda, we will use the physical radiance obtained by the manufacturer for the tungsten lamp, and we multiply it by the exposure time to plot the solid line, which is the physical radiance. And for the dashed line, it's a relative radiance, which we can get from the MATLAB result I just can't explain. So the distance between them is a shifting constant C lambda, and we can get that by using the equation. There's one. And for the shifting constant without filter, we'll do the same thing, but without filter. So since the physical radius for the images with filter is equal to the image without filter, so both equations will be equal to each other, which means taking image with filter is equal to taking image without filter. So we want to correlate CI with C lambda, and we'll use the least square function to minimize the error to 0 and solve for CI. For our experimentation, For our experimentation, the flame will be set up in a dark room to avoid any light that can affect our result. Then we will take multiple images, different exposure time. Then we will use our image use our MATLAB code to find our temperature using Planck's law. Then we will generate a lookup table and compare our temperature with the true temperature of the flame. We can find the percentage error, and by that we can know the high percentage error is the picture that have a high saturation limit and low saturation limit.
For verification only, we will use the thermocouple to measure the temperature, and then we will compare it with the results that we get from our MATLAB codes. Our budget for this project is $500, and we have one equipment to buy, which is a tungsten lamp, and it costs $750. So we are over budget. Unless we request for extension and get the $250, so we will be on budget. Here are our equipment that are going to be offered from Dr. Ghamari, which is the camera, flame setup, and thermocouple. And for our Gantt chart, we have accomplished the development plan and image processing and camera calibration relative. And we will order tungsten lamp by next week, and we will be ready to start doing our experiment.
These are acknowledgements. I would like to thank Dr. Bednars, Dr. Nazar, Dr. Saroj, Lisa, Siddhant at University of Buffalo, who did a similar experiment for flux calculations, and Luigi. These are references. Thank you. And any questions?
So, I'm very impressed with the depth of your knowledge on the subject. I'll start with the one part observation I actually did understand. Green is not a primary color, so I know that from working with my kids and all that. Yellow, blue, and red. Remember, you had said green is primary color. So that was a joke. Okay. I did want to know though, how many of the equations came from your standard heat transfer course, and how much of this did you have to research on your own and through Dr. Ghamari or what? Because I was very unfamiliar with the majority of your equations.
Yeah, like this equation that you see will be is there in a heat transfer book, and this one. That's it.
Yeah, it's basically based on Planck's law, which we learned in heat and mass class.
And yeah, this one is also what we do in the radiation chapter in heat transfer for a diffused emitter. So these are the only two equations that come from our book.
And everything else you have research?
Yeah, we had to do
For
research.
this project?
Yes. Any other questions? Dr. Zoom?
Okay, so how many lines of transport do you have right now?
We have about, like, we are still working on optimizing it so that we can increase the number of pixels so that our data can be more accurate. But right now we wrote like 3 subroutines and 1 routine.
How many lines roughly?
Like I believe we are about 100 maybe.
What do you expect eventually? How many lines roughly you will have to get this done?
By the end of, like, we will have 2 MATLAB code, one for calibration and one for temperature calculation.
Okay.
So I think we'll be around 200 maybe. I mean, I want to work on the optimization in next semester, and maybe we'll add some more lines or reduce some lines. So it will be, a rough estimate would be like 200 something.
This competition is completely offline, right? Not real.
Yeah, completely offline.
So you take a whole bunch of pictures at different filters, and you combine them
In the MATLAB.
offline process and try to calculate your temperature.
Yes.
So I have a final question. At the end of next semester, you get a whole bunch of data. How do you know if it's right or wrong?
That's why we are going to use thermocouple for verification. Like, thermocouple is not completely accurate, but what we will know is if it is in the right ballpark.
How do you use thermocouple to measure the
Like,
flame?
we do it at multiple points throughout the flame. So things change, like flame is not still.
Normal, like a routine practice?
Yeah, it is.
That's how you measure the
Yes,
thermocouple?
yes. For flame. That's like there are other methods like infrared or infrared camera or spectrometer. So we are going to ask the physics and the environmental department because they have them, but we are not sure if they will work for our range of visible, like the visible range that we are looking at.
Is it possible that you find a research paper with the image you can use and with the results, you can use that as a validation?
Yeah.
That's better than your, I'm not saying your,
Yeah, no, I agree.
that's really, I think if you start with that, that's going to really help you kind of validate your code, right? So
No.
Like, otherwise, you like, where does the error come from my experiment or from my code?
Yeah, no,
You can find that could be a intermediate process.
Yeah, that's
just
our-
knowing like with these random results and validate your code and go back into the experiment.
Yeah, that's our plan for the December, this December, to find research papers which have temperature profiles, so that we can even use that for verification.
Thank you.
Last question. So it's more of a comment, just build off what Dr. Seuss said. Regarding research, I'm in academics right now. Don't be afraid to reach out to authors. There's no reason to work on this in a vacuum. Collaborate, reach out to people, say, hey, I'm doing this. Let's work together. Let's further this research. This is really cool research. That's all I'm going to say is don't be afraid to reach out to people and work on collaborating.
Thank you.
Excellent project.
Thank you.
Thank you.